I've always been fascinated by flying wings. No tail, no fuselage, just a single, seamless, efficient wing slicing through the air. They look like something out of science fiction. But the truth is, the concept of flying wings dates back to the dawn of aviation, more than 100 years ago. In the 1910s, British pioneer John William Dunne created some of the first truly stable tailless aircraft, inspired by the flight of birds. His designs were radically different: swept wings, no tail, and a natural in-flight stability. A bit later, by the 1920s, the UK was pushing the idea further with the Westland Hill pterodactyl series, experimental research planes that flirted with the concept of flying wings long before it was fashionable. And in the Soviet Union, aircraft designer Boris Sharanovsky built a series of gliders starting in 1924 featuring a distinctive parabolic wing and a dream of ultimate aerodynamic efficiency.
A German airman is trying out his novel machine at Cologne. It is in effect a pair of rigid wings without body or tail.
But the biggest breakthrough came in the early 1930s when two German brothers, Walter and Raimar Horten, began experimenting with tailless aircraft. Their innovative designs are still considered far ahead of their time in both aerodynamics and stealth technology. Their most famous design, the Horten 229, was a jet-powered flying wing, faster and stealthier than anything the Allies had ever seen during World War II. Though it never saw combat, it demonstrated the potential of tailless, stealthy aircraft long before such technology became mainstream in modern designs like the B-2 bomber. Meanwhile, across the Atlantic, Jack Northrop was working on his own vision. His YB-35 and YB-49 bombers pushed the limits of American aerospace engineering during the 40s. Both the Horten and Northrop teams believed that flying wings, with their sleek and efficient designs, were the future of aviation. But sooner or later, they all ran into the same problem: stability. Imagine we have a wing moving through the air. As it flies, it generates two main forces: lift, which keeps it up contrasting the weight, and drag, which slows the aircraft down. There is also a natural tendency for the nose to pitch down. This happens around a point called the aerodynamic center, which is usually located about a quarter of the chord length back from the leading edge of the wing. The center of gravity is usually a bit ahead of the aerodynamic center. This helps keep the aircraft more stable. In conventional airplanes, the tail plays a big role in keeping the nose level. It pushes downward to balance the nose-down tendency of the wing. But this tail force actually creates extra drag and lift in the opposite direction, which is not ideal for efficiency. Flying wings, on the other hand, aim to get rid of the tail and fuselage to reduce drag and improve lift. But without a tail, the wing has to do all the work of controlling pitch by itself. This makes flying wings naturally unstable. In order to fix this, designers came up with clever solutions like using reflexed airfoils, which have a little upward curve at the back, swept back wings so the aerodynamic center naturally moves backward, helping the aircraft stabilize itself and wash out, which is basically twisting down the wingtips slightly to generate the nose-up moment equivalent to a conventional tail. However, back in the early 20th century, materials, technology, and sensors weren't advanced enough to make flying wings work reliably. Today though, thanks to better materials and modern flight control systems, flying wings have become possible and are used in some of the most advanced aircraft designs. But this concept isn't just found in billion-dollar stealth bomber. In the RC and FPV drone world, small flying wings have exploded in popularity in recent years. They are fast, efficient, and incredibly agile. Their lightweight designs, paired with advanced flight controllers and HD digital video links, have made these tiny little wings the perfect platform for long-range, high-speed, and immersive flight. Today, the options on the market are incredibly broad. FPV flying wings come in all shapes and sizes, and that raises the big question: what will be the optimal wing platform if what we want is to truly optimize its performance? Let's break down the problem and start with the ideal requirement for the perfect flying wing. First, we want a compact aircraft with a wingspan of less than 600 mm. This keeps the airframe small and portable, ideal for operating in tight environments and for easy hand launch. Second, we aim for a total mass under 400 grams. Similar commercially available flying wings are made from EPP foam and are normally under 250 grams. However, in our case, we'll be using 3D printing, which unfortunately comes with a weight penalty. Third, the aircraft must carry, among others, all essential systems: a flight controller for stability and autonomous flight, a GPS module for navigation, and a digital FPV system. And finally, and most importantly, we want to maximize energy efficiency. This means optimizing the airframe by carefully searching for the ideal wing parameters, the unique geometry that maximizes aerodynamic performance and minimizes power consumption. So, to design the optimal flying wing, we first need to delve into the key parameters that define its shape. The wingspan, usually labeled as P, is the total length from tip to tip. In our case, we have already fixed it at 600 mm. The chord is the distance from the leading edge to the trailing edge of the wing. For trapezoidal wings like ours, we only have two unknowns, the root chord and the tip chord. And finally, the sweep angle. This is measured along an imaginary line positioned at 1/4 of the chord. So out of these four parameters, we have three unknowns or degrees of freedom in the design, but we can reduce them even further by considering a few critical derived metrics. The wing surface area is defined by this formula, and since we have already fixed the total mass of the aircraft at 400 grams, and based on typical wing loading around 5 kg per square meters reported in the literature, this leads to a wing surface area of approximately 0.08 meters square. With all this, we can then introduce two fundamental dimensionless parameters in wing design. First, we have the taper ratio, which controls how much the wing narrows towards the tip. And second, the aspect ratio, which in our case is already fixed at 4.5. This value is also typical for small flying wings and provides a good balance between efficiency and maneuverability. So out of the original 3 degrees of freedom, we have managed to fix one more. We are left with two free parameters that define our wing's planform. On one hand, we have the sweep angle, which will vary from 0 degrees, a straight wind, all the way up to 40 degrees, in order to explore a wide range of geometries. On the other hand, we have the taper ratio, which will sweep from 0.2 up to a maximum of 1. Once we have defined the parameters of the wing planform, it's time to look at another key factor in wing design, the wing twist. We have previously talked about washout and how crucial it is for achieving a stable configuration in tailless aircraft. In our case, to control the twist along the span, we'll parameterize the angle of incidence at 3 stations along the semi-span of the wing, one at the root, which we'll call zeta 0, another one at half the semi-span, zeta 1, and finally one at the tip, zeta 2. To recap, we now have the following final degrees of freedom: sweep, taper, and the twist, defined by 3 angular values. So the question is, what's the optimal combination of these 5 parameters to achieve the best performance? I then jump into my favorite CAD software and I spend quite some time generating a parametric 3D model of the flying wing, allowing me to easily modify each one of the 5 degrees of freedom. You might also notice that I have added some vertical wing tips. While that topic deserves a dedicated video on its own, just keep in mind that these surfaces represent the bare minimum required to ensure sufficient yaw stability in our tailless design. But here's the problem. In order to find the optimal combination of parameters that maximizes performance, we will need to fully explore the design space and evaluate all possible combinations of these 5 variables. Even if we greatly simplify the problem and only consider 20 values per parameters, we are still looking at over 3 million designs. Running full aerodynamic simulation for each one will be incredibly time-consuming, if not downright impossible. Just to give you an idea, on my modest desktop computer, each CFD takes around 8 hours to run, and for each geometry we need to simulate 3 different angles of attack to extract key aerodynamic coefficients like the lift curve slope, the drag polar, or the pitching moment derivative. At that rate, it will take over 8,700 years to explore the full design space manually. So clearly, this kind of brute force search isn't viable, and that's where artificial intelligence comes into play. To train the AI, I first generated around 50 different designs that will give us insight into how each of the 5 parameters affect the aerodynamic performance. Each of these 50 designs represent a unique combinations of sweep angle, taper ratio, and wing twist. Together, they will help us explore how each variable and their combinations affect aerodynamic efficiency. This initial dataset is crucial. It's what the AI uses to learn how the design behaves across the entire parameter space, and it lays the foundation for the later optimization. Okay, so now we have our 50 geometries and an insane amount of CFD data. Results generated over the course of several months with my PC literally smoking. So what do we do with all this data? If only we had a sort of entity capable of recognizing patterns. Exactly, you name it, a neural network. A neuronal network is a type of machine learning model inspired by the way the human brain works. It processes information through layers of interconnected neurons that learn from examples, just like we do. In our case, we feed the neural network with the 5 parameters that define each wing shape, and since it has been trained on our own CFD dataset, the network can now predict key aerodynamic values for each design, things like lift, drag, and the pitching moment coefficient. This means that we can now explore thousands of new combinations in just seconds, rather than spending weeks running time-consuming simulations. Going back to our problem, we now have a neural network that can predict the performance of any wing design almost instantly. But we are still left with the same question: among the infinite combinations, which one is the best? This is what we call an optimization problem, and to solve it, we'll use an evolutionary algorithm. An evolutionary or genetic algorithm is an optimization method inspired by natural selection. It starts with a population of random designs, evaluates their performance, and then combines and mutates the best one over several generations, gradually evolving towards the optimal solution. The result is the optimal combination for our 5 design parameters, and at this point we need to ask, is this combination different from the one in the previous iteration? If the answer is yes, then we proceed to run CFD simulations on both the current optimal geometry and the point of highest uncertainty predicted by our neural network. This allows us to enrich the dataset with new valuable information, retrain the neural network, and perform the optimization once again. However, if the new combination is identical to the previous one, it means that we have likely reached the optimum of our objective function. And with that, bingo! We have found our final geometry. Now, this entire process from CFD data handling to training the neural network to running the evolutionary optimization was implemented in Python. And let me tell you, it wasn't exactly a walk in the park. But don't worry, I won't bore you with the details here. The implementation side is well beyond the scope of this video. The important thing is, I made Python finally bend to my will. And after crunching numbers for hours, fueled by nothing but code and caffeine, I finally uncovered the magical combination of parameters behind our ultimate flying wing design. With the number crunched and the optimal wing born from the AI, all that was left was bring it to life. So once again, I dove back into my CAD software, this time to design a detailed model of the airframe that would be fully 3D printed. This wasn't just any model, it had to be tough enough to withstand the forces of flight, but light enough to meet our strict weight limits. But after countless hours of refining and redesigning, the digital dream was finally ready for the real world, and with that, we were ready to build. With the airframe complete, it was time to install all the essential hardware. The servos that will move the elevons are mounted directly onto 3D printed covers, which are screwed into the main wing. They sit on top of the wing to prevent damage during hard landings. You might have noticed some grooves running along the wing. Those are actually designed to house an LED strip, just for that extra futuristic touch. As for the electronics, the setup is surprisingly straightforward. We've got an electronic speed controller responsible for regulating power to the brushless motor. The motor is embedded directly into the rear of the wing to keep the airframe as streamlined as possible. Then comes the brain of the flying wing, a MatTech flight controller running on ArduPilot, which is connected to an ELRS nano receiver, and a GPS module that will enable us to perform autonomous flight. There is also an XT30 connector for the main LiPo battery, and of course, all the necessary wiring that will later be hooked into the FPV system. For the FPV system, I'm using the DJI-04 Pro, a high-performance digital setup known for its low latency, 4K image quality, and a reliable long-range video transmission. It's perfect for immersive flight and high-quality footage. The entire system is mounted in the nose of the airframe, which is easily removable, making maintenance and access incredibly simple. And thanks to its modular design, I can 3D print different nose sections to accommodate a wide range of FPV systems, whether analog, digital, or anything that comes next. And finally, with the aircraft hooked up to my computer, it was time to calibrate the flight controller, setting up sensors, defining control surfaces, and teaching ArduPilot how to understand the airframe in general. So one last check and we are ready to fly. Finally, the day had come, the first flight. I won't lie, I was quite nervous that morning. After months of designing, testing and building, it all came down to this single moment. Would it fly? Would everything work as planned? This was it. There was only one way to find out. I can only say this, it flies beautifully, stable, fast and incredibly efficient, just like we hoped. If you guys are interested, you'll find the link to download all the 3D printed parts down in the description. Thanks for joining me on this journey and don't forget, stay curious, stay creative and keep building the future. See you in the next one.